of m of g, because a star is a function from this product to m of g, so that for any mu and mu in m of g, mu star nu must be an element in m of g. Mu star nu is an element of m of g. But by the Rees representation theorem, we know that m of g equal to the dual of c0 of g. Okay, I recall again that for any locally compact topological group we have this equality, m of x equal to the c0 of g, c0 of x prime, or c0 of x star, the dual of this space. Okay, so in any locally compact group we have this equality again. So mu star nu must be an element of m of g, or must be an element of this dual space, so that we can consider this element as n functional on c0 of g. Okay, for any f in c0 of g, we define mu star nu of f equal to mu, or these two are two notations for the same concept. Okay, mu star nu of f, mu star nu of f, these two are the same, but these two defined by this equality, the integral of fxy, the mu x, then the mu y. Okay, by this definition we define mu star nu as a function from c0 of g to c, and it is easy to see that this is a linear function and it is a bounded function. Okay, so that mu star nu is an element in the dual of c0 of g, and so this is an element of m of g by the Rees representation theorem. Okay, by this approach we see that we consider mu star nu as a functional on c0 of g. Okay, mu star nu of f equal to this integral, and in this definition we see that we need the binary operation in g, because xy must be defined. Okay, please note that in this definition this integral take on g and this on g again. Okay, so that this f in c0 of g is a function from g to c. Okay, so that this xy must be belong to g, and we must have a binary operation on g. For this reason we consider g as a group, not a general topological space. Okay, locally compact group. Mu star nu is linear and bounded, so This is a functional on C0 of G, so that this is in the dual of C0 of G or M of G. Theorem. M of G and a star this binary operation is a Banach algebra, and this is a unital Banach algebra. And I recall that a Banach algebra X and a star is called unital if and only if there exists an identity element such as E by the index X, such that for any X in X, E star X equal to X star E equal to X. Okay, and M of G is a unital Banach algebra. Unital Banach algebra. M of X is a unital Banach algebra. This Banach algebra M of G is called the major algebra of G, so that you know the definition of major algebra. This space is called the major algebra, and we know that the major algebra with the convolution is a Banach algebra. This star is called convolution, that we can define in the following. This binary operation is called the convolution operation on M of G. Let me take some definitions and recall this definition for you. Let X and Y be Banach algebras, and algebra homomorphism is a map such as T from X to Y, such that for any X and Y in X and for any alpha in complex numbers, we have these properties: T of X plus Y equal to T of X plus T of Y, and T alpha X equal to alpha T X, so that this is linear. And also we must have an addition property: T of X star Y equal to T of X star T of Y. Please note this X is a Banach algebra, and also this Y is a Banach algebra, so that X equal to X with this binary operation, one addition, a scalar multiplication, and this star. Okay, that we can denote this by a star of X, a scalar multiplication of X, and plus of X, and a star of X. And also Y is a Banach algebra, so that we have one addition, scalar multiplication and a star again. Okay, all of this is for y, so that we can write x plus y. Sorry, this is, let me correct this. This is a addition operation for x, and this is the addition operation for y. And also we can write alpha x in x and alpha in y, because t of x belong to y, and we must consider the scalar multiplication of y. But this x is an element of x, so that we must use the scalar multiplication in x. Okay, x and y are Banach algebra, so that for any of these spaces we must have one plus, one scalar multiplication, and one star. And also we have this definition that x and y be two norm spaces and t from x to y be a linear map, then the adjoint of t denoted by t star and defined by this definition. T star is the function from y star to x star, is the function from the dual of y to a function to the dual of x. Okay, by this function rule, for any f in y star, t star of f must be an element of the dual of x, so that must be act on element of x. T star of f of x equal to f of t of x, because you know that t of x is an element of y, and so f can be act on this element. F is an element in y star, in the dual of y. Okay, f is an element of y star. So since we consider f in the dual of y star, t star of f is an element of x star. T star of f is an element of x star, so that t star of f is a function, is a linear and bounded function from x to c. This is the space of all bounded and linear functions from x to c. Okay, so that this must be a linear function from x to c, so that we must define t star of f on x, and we define this t star of f of x for any x in x. Okay, defined by this equality. And since this f considered in y star, so that f is a function from y to c, this f is a function from y to c, so that this f can be act on t of x, because t of x is an element of y. So this is a well defined definition, and for any linear function from x to y, we can define a linear function from y star to x star. It is very trivial that this t star is bounded I explain again this definition, if t is a linear function from x to y, then t star is a linear function from y star to x star. For any f in y star, t star of f belong to x star, and for any f in y star, t star f is a function from x to c. And this is the definition of this adjoint, and it is very trivial that this t star is linear. I prove this in the following. Okay, now let G be a locally compact topological group and H be a closed subgroup of H if we consider T from C0 of G to C0 of H by this function rule. T of F equal to the restriction of F to H. Okay, because we know that if we consider F in C0 of G, I write in this section. F is a function from G to C. We know that is a subgroup of G. Request the domain of to H, the H to the row of H vanish at infinity, because F vanish at infinity, but this domain be restricted. Okay, so by this function rule we have a function from C0 of G to C0 of H, and this is linear. It is very trivial that this is linear. Let me write for you. We define T from C0 of G to C0 of H by this function rule. For any F in C0 of G, T of F equal to the restriction of F to H. It is very trivial that if F1 and F2 are two elements in C0 of G, T of F1 plus F2 equal to T of F1 plus T of F2. Because T of F1 plus F2 equal to the restriction of F1 plus F2 restriction of this to H, and this is equal to the restriction of F1 to H plus the restriction of F2 to H, and this is equal to T of F1 plus T of F2. So that we have a linear map from C0 of G to C0 of H, so that T star is a function from y to x, or y star to x star, C0 of H star to C0 of G star. But we know that this is equal to M of H by the representation theorem, and this is M of G, so that T star is a function of M of H to M of G. Okay, T star is a function from C0 of X star to C0 of G star, or T star is a function from M of H to M of G. And we have this equality, T star of mu star mu equal to T star of mu star T star of mu. I recall that if T from X to Y is linear, dear students, if T from X to Y is a linear map, then T star is a linear map too, because for any F and G in Y star and for any X in X, we know that T star of F plus G of X equal to F plus G of T of X, and this is equal to F of T of X plus G of T of X, but this is equal to T star of F of X by the definition of T star, and this is equal to T star of G of X, so that for any X we have this equality, so that this must be equal to this function, T star of F plus G equal to T star F plus T star G. And for any F in Y star and for any alpha in F, T star of alpha F equal to alpha T star of F. This is very trivial. So that for any linear map from X to Y, T star is a linear map from Y star to X star. And for any mu and nu in M of G and for any F in C0 of G, mu star nu of F equal to this integral. Okay, mu star nu of F equal to this integral of G F of xy d mu of x d mu of y that we defined in the previous slides. And for any G in G, we can define Dirac measure. We know that Dirac measure is a regular Borel measure, and this is an element of M of G. So by the representation or Dirac measure at G is an element of the dual of C0 of G. If we consider this Dirac measure as a functional, we have this equality for any F in C0 of G, delta G of F equal to, these two are the same, okay? Delta G of F equal to F of G. F of G. So that, please note that if we consider Dirac measure, as a functional on C0 of G, you must use this equality or this definition. Mu, this is the definition. Mu in M of G is called discrete whenever mu be in the closure of this set. The set of linear combinations of Dirac measures, okay? The set of all linear combination of Dirac measures. They are Dirac measures, okay? And they are linear combination of Dirac measures. If you consider the set of all linear combination of Dirac measure and compute the closure of this set, this line means the closure of this set, closure in M of X or C0 of G star, because you know that M of G or C0 of Gx star are norm space, okay? This is a subset of this norm space, and you can take closure. Now any element of this closure is called a discrete measure. M of G with the convolution. Convolution is the A star operation, okay? The operation A star that we define in the previous slide is called convolution operator. M of G with the convolution is a unital Banach algebra. We know this Banach algebra is called the measure algebra of G. I write this theorem with a proof for you, okay? Measure algebra. Now let G be a locally compact group, and beta is the sigma algebra of Borel subset of G. We recall that Borel sigma algebra is the smallest sigma algebra containing open sets, or the sigma algebra generated by open sets, okay? The sigma algebra generated by open sets. If two, for example, is the set of all open subset of a topological space X, then the sigma algebra generated by two is called Borel sigma algebra. This is the smallest sigma algebra containing two, okay, sigma algebra of Borel subset of X, or in this case G. Let G be a locally compact group and beta is the sigma algebra of Borel subset of G. A regular Borel measure M of G from beta to 0 infinity is called a hard measure whenever we have this property. You see the definition of regular Borel measure in the previous sessions, so that this is a regular Borel measure, but if we have an additional property, we say this is a hard measure, okay, for any G in G and for any Borel subset of G, G of G equals mg of E. This should translate in general if mu be a measure on a sigma algebra A, for example, in G and A be G invariant by this definition for any A in G and for any, for example, E in A E belong to A. You say that A is G invariant. The multiplication of any element of G in any element of A belong to A. Then we say that mu is invariant or more precisely G invariant Whenever for any A in G and for any E, for example, in A, mu of AE equal to mu of E. Translation invariant. Translation invariant. Invariant or translation invariant. Okay, invariant. Whenever we have this equality, mu of AE equal to mu of E. You know that a very important example of G invariant measures is Borel and important G invariant sigma algebra is the sigma algebra of Borel sets. Example, the sigma algebra of Borel sets in G that we denoted by beta, okay, or beta G always, is G invariant. Is G invariant for any A in G and for any E as a Borel subset of G. AE is a Borel subset too. AE belong to this sigma algebra too. Okay. Now in this definition of Haar measure, any regular Borel measure that is invariant or G invariant is called a Haar measure. Is called a Haar measure. So that a Haar measure is a measure that defined on the sigma algebra of Borel set. This is a Borel measure and must be invariant. Then we say that mu or this M of G is a Haar measure. And I recall that GE equal to this coset of E. The set of all Gx such that X is an element of E. And this is the binary operation of G again, okay? G X, because G and X are in our group G. So we need to the binary operation of G. Binary operation of G. We have an important example. Let G equal to R, real numbers, with the ordinary operation of real line, R with plus. Then the Lebesgue measure is a Haar measure. You know the Lebesgue measure on real line. Lebesgue measure. You know that Lebesgue measure maps any interval to the length of this interval. Okay. if we denoted the Lebesgue measure by lambda, we know that for any interval in R, the Lebesgue measure of I equal to the length of I. For example, the Lebesgue measure of 0 and 2 equal to 2 because the length of this interval equal 2. And in general, the length of this interval A and B equal to B minus A. B minus A. Okay? And if the first or the end of this interval be closed, we have the same length. You know this, okay? For example, the length of the open interval 0, 2 equal to 2 again. Or the closed interval 0 and 2 equal to 2. You can review the definition of Lebesgue measures in your measures book or measure booklet. But this is the important property in Lebesgue measure, okay? The length, the Lebesgue measure of any interval equal to the length of this interval. By this definition, we see that the Lebesgue measure is invariant, translation invariant, because if we consider any element in R and we consider any interval such as I, A and B, this is an arbitrary open interval, okay? G plus I equal to G plus X for any X in this interval. So this is equal to this interval, G plus A and G plus B, because for any X in this interval, we know that G plus X belong to this interval, A plus G and B plus G, so that all of these elements must belong to this interval and vice versa, so that G plus A and B equal to G plus A and G plus B. This is an interval again. Any translation of open intervals is an open intervals again. Any translation of open intervals is an open intervals again, okay? Now, if we consider the Lebesgue measure of this translation, G plus this interval, is equal to this by this equality. The Lebesgue measure of this interval and the Lebesgue measure of any intervals equal to the length of it, okay? And the length of this integral equal to G plus B minus G plus A. And you can omit this G so that is equal to B minus A by B minus A is the length of this interval. This interval. And we can write the first and the second, this interval. Okay? This is the length of this interval. So that for any open intervals such as I, we prove that lambda of g plus I for open intervals, okay, equal to lambda of I. Similarly, for any interval in R and for any element in R, we have this equality. Lambda of g plus I equal to lambda of I. It is very easy. And also for any Borel set we can prove this equality. In more general, we have this proposition for any G in R and for any E in beta. We have this equality, and we know this equality. We prove this equality in your measure theory course. And so the Lebesgue measure is a hard measure on the sigma algebra of Borel set. This is very important example. Very important example. And also we have this example. Let Rn be the ordinary addition in a locally compact group in the locally compact group R, okay, in the locally compact group R. Locally compact group R. And locally compact group R, and the Lebesgue measure so this was true. Local Rn with the ordinary addition is a locally compact group. Okay, this is true. And the Lebesgue measure is a hard measure on this group. Okay. ordinary addition is this addition for any n cube a and b, a plus b equal to this. Pointwise addition, and with the ordinary norm, distant norm in Rn. Okay. For any two elements, this is the reason for locally compactness. Okay, let me write this for you. Rn with the ordinary plus operation is a group. This group is a compact group. Because locally compact groups, because for any element in Rn, we see that this element is an element of this open interval. For example, x1 minus 1, x1 plus 1, okay, multiplied by xn minus 1, xn plus 1, and this is a subset of the closed intervals x1 minus 1, x1 plus 1 multiplied by xn minus 1, xn plus 1. If we consider one-dimensional case, this is very trivial. Okay, x minus 1, x plus 1, and then its closed interval. Okay, this is for n-dimensional case, but you know that this is an open subset, and this is compact by the Heine-Borel theorem. This is a compact subset. You know that if for any x in X we have an open set and we have a compact set such that X belongs to this open set and this open set be a subset of this compact set, or a space is locally compact. A topological space X is called a topological space X is called locally compact whenever for any element in X there exists an open subset of X and there exists a compact subset of X. Compact, okay? Such that A belong to U and U be a subset of X. Okay? U be a subset of X. And in this case we see that for any element such as A in our space there exists an open set and there exists a compact set such that A belongs to U, for example, and U be a subset of X. So that this is a locally compact group. And the Lebesgue measure is a Haar measure. Lebesgue measure is a Haar measure. You know that in Rn we have Lebesgue measure 2. Okay, dear students, do you have? Thank you very much. Thank some students not appear in our class. This is very bad. Let me write this for you. Okay.
يرجى إخبار الطلاب الآخرين بحضور الدروس. أنا قلق بشأن امتحانهم.
Do you understand? Thank you very much. Thank you and goodbye for now. Goodbye.